Hello students, this is Dr. Bhavani Regmi with Survey of Chemistry first. Today we are continuing on our chapter 4 about covalent compounds. In our last video, we learned how to name the covalent compounds, how to draw the Lewis structure of the covalent compounds. Right? So the Lewis structure gives us the connectivity, how the two atoms are connected with each other, where are the lone pairs. That much of information we can get from Lewis structure. But Lewis structure does not give us the geometry, the shape of the compound. Okay? To figure out, to know the shape of the molecular compound or covalent compound is crucial because the shape depends on the function at the molecular level. Okay, so the compounds with the similar combination of elements, okay, they can act as either toxic, or some compound with the same composition of element can act as medication, right? Whether it acts as a toxic or it acts as medication depends on their shape. That's why knowing the shape of molecule is important. Okay, pharmaceutical companies spend a lot of money on figuring out the shape of the molecules that can act as a drug or medicine for some disease, right? So today's lecture is about how can we use VSEPR theory to determine or to predict the shape of a given molecule. Okay, so when I say molecular compound, the covalent compounds are also known as molecular compound. Okay, so in today's lecture, we are going to use the theory, VSEPR theory, to predict the shape. The theory stands, the name stands as valence shell electron pair repulsion theory, VSEPR theory in short. What does it mean is, the basic meaning is when we form a formula or when we have a molecular compound, these outer atoms are surrounding the central atom, right? All of them have electron pairs with them, the bonded pair of electrons around the central atom, as well as we have some of them may have lone pair of electrons around the central atom. All these electron pairs will repel each other. You can say why? Because all the electron pairs are negatively charged, right? So when we are, let's say, drawing, let's say I have carbon and I have 4 bonds around the carbon in the Lewis structure. Okay, so let me write the Lewis structure of a methane. So I have a little far away, but you can see it. I have CH4 molecule. Okay, so each of these hydrogen atom means these electron pairs are around the carbon, right? All of them are negatively charged, the shared pair electrons, they repel with each other because same charges, they repel, right? So now the electron pairs would like to arrange as far apart as possible to give the least amount of repulsion because of negatively charged electron. That is the main principle of VSEPR theory. Okay, the VSEPR theory says that the electron pair, in order to minimize the repulsion between them, they would like to spread as far as possible. And when they spread as far as possible, they will end up making some basic shapes depending on how many electron groups are around the central atom. Okay, and we will learn and we can predict the shape of the molecule just counting the electron domains around the central atom. So the number of these bonding, and if in case we do not have a lone pair here, but if we have some molecule with the lone pair in them, the lone pair is also known as non-bonding electron pair. So the number of bonding pair and the non-bonding pair will determine the geometry, the shape of the molecule around that group. Okay, so let us understand how to use this theory to come up with the basic shape. So the theory says that, okay, if we have two electron groups around the central atom, then how would they like to stay, right? Let's say we have a carbon in the center and then we have two electron groups around it. Okay, how do we count electron group? It's like one bond with hydrogen. This is one kind of electron group. And then we have the bonds with nitrogen, right, from the carbon, the other electron group. We count this as 1 and 2. So all together we have two electron groups. The two areas, they share the electron with the central atom, right? One area and the another area. Either it is double bond, triple bond or single bond, we count that as one electron group when we count the sterics. Okay, it is like we are counting the traffic around our central carbon, which is our transaction area. Okay, so we have two electron group here, one here and one here, total two electron groups around the central atom. Then the theory says these two outer periphery atoms would like to stay as far as possible, okay, all the way as far as possible, and now they give us the stable arrangement. They do have least repulsion between them, and while staying far apart from each other, if there are two electron groups, then they will make 180-degree bond angle. Okay, it means the outer groups are 180-degree apart from each other. Okay, we call as the bond angle is 180-degree, and the shape of the molecule will be a linear shape. Okay, we also call geometry for that. So if we have two electron groups around the central atom, okay, and the central atom does not have any lone pair, then we have here the linear geometry. Okay, so now how do we, some other examples of here is, we have here HCN, right, for the linear molecule. Similarly, CO2, carbon dioxide. If we draw the Lewis structure of carbon dioxide, we have to place the double bond on the central carbon to the outer oxygen, and the oxygens will get lone pairs in them, and we do have a linear molecule. Because we count this as there are one group and there is another group, two groups around the carbon. So we have, they would like to stay far from each other, right? If you further bring them closer, they will be much closer than 180-degree. This is the farthest that they can be. And now we have a linear geometry. Okay, so the electron geometry means the electron groups are at linear fashion, right? The molecular geometry, the shape of the molecule will also be linear, okay? And the bond angle is 180-degree. Okay, so one hint that I would like to give you is whenever there is no lone pair in the central atom, the two electron domain, all of them are bonded pair of electrons. In that case, the electron geometry and the molecular geometry is same thing. Okay, both of these are linear in this case. Now, let's look on what if we have three electron groups around the central atom. What will happen? Okay, so if we have three electron groups around the central atom, then now we can see with this example here, we have CH2O, there are 1, 2, 3, right? There are 3 electron domain, 1 domain, 2 and 3 different electron areas around the central carbon, all 3 of them pushing each other because they repel. Now the most comfortable way of sitting down and have a stable arrangement is by making 120 degree. Okay, so more or less they will make 120 degree bond angle between them. Okay, so when they have 120 degree bond angle between them, it means they are having an electron geometry of trigonal planar. Again, the central carbon does not have a lone pair. All of the 3 electron domains are the bonded ones. You can guess the molecular geometry for this molecule will also be trigonal planar. Okay, so the bond angle is 120 degree. You want to memorize the corresponding bond angle for each shape. Okay, so earlier was linear 180 degree. This is trigonal planar 120 degree. How did they get the name trigonal planar? Is these 3 electron domain would like to spread as far as possible as if they are heading towards the 3 vertex of the triangle, right? That's why the name trigonal. It came from the triangle, trigonal. And all these atoms will be on the same plane. That's why the name is planar. Trigonal planar means you have a flat molecule, right, with 3 atoms facing 3, showing 3 vertex of the triangle. Okay, so we have here the 3 groups around central atom, trigonal planar. Now you might ask, what if among these electron groups one of the location is occupied by the lone pair? Now the shape of the molecule, the molecular geometry will be different from the electron geometry. Okay, so let me go ahead and show you. In this case, the electron geometry of your SO2 molecule, okay, it will be still trigonal planar. Okay, to count the electron geometry, we count how many electron areas are around that. So we have 2 bonded area and we have 1 lone pair, right? So altogether 3. Whenever we have 3 sterics, right, we have 3 things around the central atom, every time the electron geometry is trigonal planar. Okay, now the molecular geometry, it will not account the lone pair in the name, but it will account the impact of lone pair. What do I mean is the molecular geometry of SO2 molecule will be bent because you will have 2 bonded atoms, right? So only these will be involved in to give you the shape, the name of the shape. But how far they are from each other is impacted, is influenced by the lone pair. The lone pair will occupy more space, okay, and then it will repel those bonded pairs further away. So what will happen is now those bonds will be away from the lone pair and now they will be more closer to each other, lesser than 120 degree. Okay, that's why we have here the bent molecule. They are not in linear because they are pushed closer by the presence of lone pair. Okay, so you can see whenever we have a lone pair in the central atom, in that case the electron geometry and the molecular geometry, they do not have the same name. Okay, it will be different. And what will be the molecular geometry depends on how many atoms are bound to the central one. In this case there were 2 of them, so it is a bent shape. Okay, so the molecule SO2 makes a bent shaped molecule. The CH2O is a trigonal planar molecule, the shape of the molecule. Okay, both of them have three things around them, three electron domain around them. That's why both of them have the name electron geometry trigonal planar. Okay, I guess I explained everything that you need, and the bond angle is 120 degree, almost 120 degree in this. Okay, it could be a little bit lesser than 120 degree, but for our level, if you answer that they are around 120 degree, that is good enough. Okay, we do not need to go for that very small delicate differences in them. Now, next question. What if we have four electron domain, four electron groups, four groups around the central atom? What will be the case? Let's try this one. We have methane, right? We have a carbon in the center and four hydrogens around it. When we draw the Lewis structure of methane, we draw carbon in the center, four hydrogen on the four side, right? We draw as if they are 90 degree from each other, but in reality, they are not at 90 degree. They are 109.5 degree apart from each other. Okay, the reason is you have four domain, you have four electron groups around the central, right? You have four things around the central. So I'm circling each of the electron domain here. Okay, each of the domain here, 1, 2, 3, and the fourth one is here. Somehow the pen is not working. So we have four electron domain when surround the central atom. They will repel each other. If they stay at 109.5, then their repulsion is minimized. Okay, repulsion is much less at that time, and that gives it a stable arrangement. So we have 109.5 bond angle when we have four groups around it. Since we have steric number 4, we have four different group numbers. Okay. Sorry, I'm doing something distracting here. Okay, four different groups here. Our electron geometry is tetrahedral. Okay, tetra means four, right? Hedral. Tetrahedral means these four groups are heading. Okay, they are facing the vertex. Okay, they are facing the four different vertex of a tetrahedral structure. Tetrahedron. Okay, tetrahedron has the four face. So we have here the tetrahedral geometry for the molecule over here. Now, since the central atom does not have a lone pair, okay, the molecular shape of the molecule will also be tetrahedron. Okay. So tetrahedral bond angle will be 109.5, and the examples are CH4 molecule we just saw, CF4 or CHCl3 or ammonium ion. In all these cases, the outer atoms are at 109.5 degree apart. Okay, so you might be asking, what if we have deviation in the shape? What if we have lone pair in the central atom? Right? One of the position of the tetrahedron is occupied by lone pair. Now, the molecular geometry of such structure will be different from the electron geometry. Okay, so let's see that example. Example is, if we have one lone pair and three are the bonded pairs, in that case, the top of the tetrahedral, the apex of the tetrahedral will be occupied by the lone pair. And when we draw just the molecule, okay, just the atoms bound to the central atom, then the structure will become trigonal pyramidal. The electron domain geometry will still remain tetrahedral because we have four things around it, but molecular geometry will be now trigonal pyramidal. There are three of them, right? But they are not on the plane. So that's why one of the lone pair is pushing those three closer to each other. Okay, so they are lesser than 109.5. Okay, so we have here a situation where bond angle is lesser than 109.5. But if you write 109.5, you are good. Okay, examples are hydronium ion and ammonia. Now, let's see one more case where we have two lone pair in the central atom. Okay, if we have two lone pair and still the total number of electron domain is 4, then we get a case similar like this. This is the case of water molecule. Okay, if you just draw the oxygen and hydrogen, just have the shape of the molecule, it will look like a bend because the shape is given by just the bonded atoms. But where they are, what is the angle between them is influenced by the lone pair. Okay, so here the lone pair will undergo more repulsion, right? So they will push these bonds closer, and then now it is lesser than 109.5. So electron domain geometry, when we have 4 groups around the central atom, it will stay as tetrahedral, but now the molecular geometry is a bent one, or if you write inverted V shape, it is a bent one. And we have the examples like water and H2S molecule. Okay, so putting all these information together in a table, we have a summary here. Okay, now let's see the things that we just learned. If we have two things around the central atom, both of them are the atoms, we have no lone pair, then they will be linear, right? 180 degree apart, and we have examples here. If we have 3 things around the central atom, all of them are atoms, there are no lone pair in the central one, okay, then they are in a perfect 120 degree apart, and then they are trigonal planar shape. If we have perfect situation, again 4 electron domain, all of them are bounded atoms, there is no lone pair present in the central atom, then electron domain geometry is tetrahedral and the shape of the molecule is tetrahedral. Okay, all 3 cases we saw here, all of them are the electron domain as well as the molecular shape will be the same name, right? Trigonal planar, the electron domain geometry, trigonal planar, the shape of the molecule, tetrahedral, the electron domain geometry, like example methane. Tetrahedral will be the molecular geometry. Okay, now we have deviations, two important deviation from the tetrahedral shape. Now, out of 4 groups, if 3 of them are bonded atoms and 1 of them is lone pair, then it becomes the shape of the around the atom is trigonal pyramidal. A good example is ammonia. We saw it. If we have 2 lone pairs and we have 2 bonded atoms, then this molecule becomes a bent. It never becomes a linear. Okay, it will be bent. There is no 180 degree. It is just 109, almost 109, closer to that, less than that bond angle there. And we have 2 lone pairs there. Example is water. Okay, so this was the summary for the shape of the different molecules. Now, using the VSEPR theory, the theory that tells like, okay, the atoms would like to spread as far as possible so that to minimize the repulsion between their electron pairs, and by doing that, they come up with a certain stable structures, and we call them shape, right? So that is what we learn here. So here we have some examples for you to practice. Okay, more important is look on these examples given in the slide, practice them, draw the Lewis structure first, and then think about how many atoms are around the central atom and how can you make a stable arrangement for them. All right, so you can practice on them. I will show you one of this geometry because we have here a larger molecule. So I will talk about that. So determine the geometry around each central atom. The first one is C2H4. Let me pick up that. As I mentioned, these are the organic compound. You always want to make the carbon chain. Okay, the 2 carbons are there. So I wrote 2 carbon chain in a chain, and now fill up the 6 hydrogen. In order to do the Lewis structure, I will simply make the 4 bonds around each carbon because we know carbon will make 4 bonds, right? So I give 4 bonds for each carbon. Now I have 6 hydrogen to place around. So I place hydrogen here, 1, 2, 3, 4, 5, 6. So I place all 6 hydrogen around 2 carbon, and this is my Lewis structure. The question will tell me determine the geometry, means give me the angle or give me the molecular shape around each central atom. In this case, we have 2 carbon and both of them are in the same pattern, right? They are in the similar environment. So we can call this one as a central one or this one. It does not matter. Both of them have the same environment. So for carbon, we have, let's count how many domain, how many electron areas are there. Okay, so we have here 1 electron area, 2 electron area, 3 electron area, and now all of this is just 1 because there is 1 bond, right? A bond attached all them. So we have 4 electron domain area around the central carbon. So whenever we have 4 groups, then they will make, can you guess which one is this? They will make tetrahedral. 4 domain around it and all of them are bonded. There is no lone pair in it, so that it is tetrahedral shape. If the question asks you what is the electron domain geometry for this molecule, okay, around that central atom we are looking at, it is again the tetrahedral. Okay, both electron domain geometry and the molecular geometry have the same name because it does not have, the carbon does not have a lone pair. So it's good, right? Let me draw one more example. Okay, the last one. Let's pick the last one. It has CH3OH. So I am going to write the molecule, the Lewis structure for that. So I have carbon. Okay, I will go ahead and make 4 bonds around the carbon. Then I cannot write hydrogen in the middle. Hydrogens are always on the periphery. So I will just put 3 hydrogens right here because I have a room for them. Okay, I used up these 3 hydrogens attached to this carbon. Now I have oxygen and hydrogen. I can place oxygen in the center. No problem with that. I just cannot place hydrogen there. So this is the Lewis structure is not complete because I need to give or add 2 lone pairs on the oxygen. So hunk oxygen is making 2 bond here and 2 lone pair, right? Altogether there are 8 electrons. So Lewis structure is good one. Altogether we have 8 electrons around carbon. So this is also good. Carbon and oxygen both have 8 electrons. They are happy there. Hydrogens, they are happy with 2 electrons. So this is a correct Lewis structure. We are not done yet. After drawing the Lewis structure, we need to know the geometry, the shape around the central atom. Right? Let's say the question is talking about this carbon and considering this carbon as a central atom. Okay, let me write this label. Let's give this A, and let's say the oxygen is B. We will talk about oxygen in a while. First, let's consider the geometry around carbon, around A. Okay, around carbon, I have 1, 2, 3, 4 groups. So I have 4 groups. So electron domain geometry is tetrahedral. The shape, I will write only the shape. Okay, the molecular geometry is the shape. The shape is tetrahedral. Okay, around B, let's find out. Okay, B is for oxygen. Around B, we have 1, 2, 3, 4, right? So around oxygen, I have 1, 2, 3, and 4. You can either write this one or everything is 4. So I have 4 electron domain. So if the question is asking for electron domain geometry, I would say tetrahedral. That would be correct, right? So let me write here, electron domain geometry, it's tetrahedral. Okay, but about the shape, okay, the shape is not tetrahedral because out of 4 groups, 2 are bound ones, 2 are lone pair. In that case, it will be bent shape, right? Because we understood this from our earlier learning. If we have 4 electron domain, but out of 4 electron domain, 2 are lone pair, 2 are the bound pair, electron shared pair, then it becomes bent shape. Okay, so that is how we answer this question. If somebody has question on the first one, what would be the electron domain geometry? Okay, so I will just write it is a tetrahedral. So they are same in the case of carbon, right? They are different name in the case of oxygen. I think that will help you to see the difference. Okay, so please practice to do the Lewis structure and determining the shape. Okay. Let's see what we have in the next slide. And I think that might be a point to stop if we... Okay, yeah. So the section about electronegativity and bond polarity we will cover in the next video. Okay, so what we have learned in today's lesson is we apply VSEPR theory to come up with the shape of the molecule, to determine the shape, right? So this slide, the summary, it is very important understand every part of this slide, okay? And keep on exercising it. Thank you.